In this video, we're going to discuss how to calculate the percent impedance of a transformer using what is called the short circuit test. Now, in my over 20 years in the trade, I've never actually done this test out in the field. I've done it as a teacher in a classroom. So it's something that's not very practical, but it is a good example of how we come up with that number for percent impedance. And percent impedance is very important to us as electricians because that's what determines how we parallel our transformers. Remember, the three rules for paralleling are that you have to have the same voltage rating, you have to have this observed same polarities, and you have to have the same percent impedance. So we're going to show how that's calculated, use what's called the short circuit test. Now, a good place to start with anything, especially when you're dealing with transformers, is to work out ratings. Now, I've given you the rating here. I've told you that this transformer here is a 4160 volt to 120, meaning the high side sees 4160, or you can see a maximum of 4160 volts. The low side will see 120 volts, and it's rated at 20 kVA, which means that each winding here can handle 20 kVA. So we're going to use 20 kVA, divide that by 4160 volts to determine that we have a maximum rated current of 4.8 amps that can run safely through the winding here. Anything over that and you risk burning out the windings. This next calculation isn't necessarily necessary, but just to make the point that when we have 4.8 amps running in the primary side here, so if we have maximum current flowing in the primary side, we are also going to have maximum current running through the secondary side. Very important because we have what's called a shunt bar here. Your shunt bar needs to be able to handle that maximum current because we will be taking this guy up to its maximum current on the primary, which does mean that you will see 167 amps on the secondary. So it's just something that you need to be aware of. All right, so what we're doing now is we're taking this AC supply and we're going to very slowly start cranking it up. So we're going to start increasing our voltage until our ammeter that we have connected here in series is reading 4.8 amps. So slowly raise this voltage up until we read 4.8 amps. Then you notice we've got a voltmeter across the winding here. We're going to take that voltmeter and read what voltage it takes to impress 4.8 amps on this side. Now, it's not going to take very much voltage. I know 104 volts is not very much considering that it can see 4160 volts, but keep in mind it has a short circuit here, and from previous videos we've learned that the secondary side is what controls the primary's current. So there's very little resistance on this side, which therefore means that this current's going to go up, which is going to increase that current as well. So I'm telling you that, and this is a number that your voltmeter will give you, or I'm going to tell you in this video that as we cranked it up to 4.8 amps, that your voltmeter here is reading 104 volts. There's no calculation for that. It's just a reading that you will get. And now comes time to use the formula for percent impedance. We have the formula here. E short circuit divided by E rated equals percent impedance. Our short circuit voltage is this, the 104 volts that it took in a short circuit condition to reach rated current. 104 volts. Our rated voltage is 4160 volts. So we're going to take 104 and divide it by 4160. 104 volts divided by 4,160 volts gives us a percent impedance of 2.5%. So now we have all the ratings for the transformer. We have the kVA rating, we have the voltage ratings, and we have the percent impedance ratings. This percent impedance will become very important in another video where we use it to determine what the fault current available to the transformer is based off of the percent impedance.